Now we are going to explore gradient descent, vanishing and exploding gradient problems. So gradient is easy to vanish or explode. What do we mean by vanish? Because there are several layers in a deep neural network, you have several layers, and each layer has an impact on the layer before it. So in the previous lecture, we discussed that the hidden layer, the nodes in the hidden layer and the weights between the hidden layers are chained. For example, you can see here, if we are to find the partial with respect to weight value wkj, we can see it has an impact of the output node, the target, the output, and the hidden layer output here. So here we have output h. For example, this has output n and j. And we found out that when we want to find the partial here, update the gradient, then this previous output is multiplied here. And then if we move forward again to the previous layer in the back propagation algorithm, we can see that we have to know, starting from nk, then ji, then np. nk, ji, and np. So this term over here will be a multiplier of several different terms. Too many terms are multiplied here. And here we have nodes from 1 to k. So all the values from 1 to k will be considered. And then again from 1 to j will be considered in finding the partial over the first hidden layer weight matrix. So that all the terms will participate over here. They will be multiplied with each other, such that we can find or update the gradient at this point. So we have too many terms that are multiplied, and when we know that we have multipliers, so if some of the values are very small, so the gradient will become very small. So 0.25 when multiplied 4 times, it will become a very small value. And if the update of the gradient is very small, gradient descent value is very small, the weights are updated so a small value updates the weights very little update to these weights. So if we have a smaller update, then the learning is very small. However, in the case if the gradient is very large value, then the large value, when it is multiplied the gradient becomes very large, because of the fact that all terms are estimated because they are multiplied by multiplying them. So the gradient value becomes either very small if some value of the gradients are very small, and it becomes very large if some of the values are very large numbers. So why gradient descent, gradient exploring when we have very large values of gradient updates? Why is it not feasible? Because a big jump in the gradient descent method can cause divergence, which means failure of learning. So we studied that if we take learning rate, we studied it is very large values, so it is not stable. Similarly, if the gradient is updated with very large values, there's a big jump in the gradient descent. It also causes divergence, and the model is failed to learn. So the solution around the gradient exploding problem is that you can use a smaller learning rate to update the weight values because we are going to handle the large gradient values. However, we know that very small value of the learning rate causes slow learning. Nevertheless, it is one good way around the problem of solving the large gradient update values. So we can solve the gradient exploding problem by using a smaller value of our learning rate. So this is one solution that we have in addressing the gradient or exploding problem. So now comes, what is the gradient vanishing problem? So very small learning rate aggravates the gradient vanishing problem. Small gradient will lead to very slow learning of the model. So we can find a solution another way. Don't make it too small. So for exploding gradient problem, use a smaller learning rate. For vanishing gradient problem, if the gradient is very small, use a not so small learning rate. So activation functions are one of the key configurations in our deep learning model. So choosing the appropriate activation function is a key element, key aspect in the learning process of our deep learning model. So the major terms are derivatives of the activation function. So we know that what we did was we took the partial with respect to of our sigmoid classifier, and we have these terms because of the activation function. So we know that each node has a summation part and it has an activation part. So this line represents an activation function. So two parts are there. One is the summation and the other is the activation function. And whenever we are taking the partial of the activation function, we write it in this nice representation. So first, here the weight update with respect to the error update with respect to your weight kj. This portion represents your sigmoid partial with respect to weight. And then we have in the next part, we will have not only the output will play a role, but also we have, so for example, we have an output here. So this will only have this part, the on 1 minus nk. But here we have not only, or H part but also the effect of our output part. So when we are here, it will have these two values, and in the next part we have three. One is the output, one is wait update here, and one is wait update here, and all of these nodes have an activation function. We are considering that all nodes have activation function. Therefore, when we take the partial, we have this nice representation. So majority of the terms that we have here to update the weight values, taking the partial, are basically derivatives of your activation function. So what can be another activation function? Instead of your sigmoid classifier, there is one more activation function, that is the rectified linear unit or Rayleigh rectifier. This is a well-known used activation function, and essentially what it does is, if your value of x, this is your classifier as we defined before, if if x is greater than 0, then retain the value, and if it is a negative value, and for all the values it is 0. So keep it x, otherwise it is 0. If it is greater than 0, then x, otherwise 0. So by this point we know, and it can be graphically represented in this form. So below 0, the value will always be 0, and when it goes a value above, for example at 5, the value will be 5. It will have the value of x. So you are increasing the value, and your x, f of x, will return your x value. It is a linear classifier. So we have a linear representation here. Retain x, otherwise 0. So we know that weight update here, then partials, then there you have 3 multiplications up till here, and then when we go to this update, then we have 4 multiplications up to here. So all of them are multiplied. So workaround, instead of sigmoid, could be your Rayleigh activation function, where you retain the value of x rather than passing it through a sigmoid, like this sigmoid. Here is your x. This classifier, instead just keep the value of x, but if it is less than 0, or if it is any other value less than 0, then you remove that value. So what are the advantage of using this approach? You will not have a vanishing gradient problem, because your value of function sigmoid classifier will be between 0 and 1, right? The output. But for your Rayleigh activation, you will have a value of x or 0. So we will have no vanishing gradient problem. All the values of x, or you can say terms, are multiplied simply, and they do not cause the vanishing gradient problem. So another aspect of using the Rayleigh activation is that we have sparse activation in a randomly initialized network. Only 50% of the hidden units are activated. What do you mean by that? So if your value of x is any value other than x is greater than 0, it will be assigned a 0. So if you multiply the value of your activation function to be 0, that means that link will no longer be active or participate in updating the model. This is what we call the activation of your link. So that node where the output is 0, that node where the output is 0, because of your ReLU activation, it will not be activated. So in randomly initialized network, nearly 50% of the union units are activated. Random initialize. So automatically we are trying to reduce the number of links that will be active on a network, and it is 6 times faster than your sigmoid function. However, there is a problem of knockout. So what is the knockout problem? It might be possible that some links or some values may never be used in the network, or they will never be used to train your network. So this is a problem. So therefore we say that ReLU units can be fragile. What if a node is never fired for all the data points? It always gives a negative value. So the network is never trained. For example, if a large gradient flowing through a ReLU, it makes big updates of the weight. And your weight can be located at very bad points where the node will never activate on any data point again. You may find that as much as 40% of your network can be dead if you keep the learning rate too high. So learning rate is key point, so that you have to set the learning rate efficiently, so this problem is less frequently occurring in your training the network. So there is another version of your activation function, that is the leaky ReLU. Instead of using, because we could have a problem that some of the nodes will never be used to train, or the inputs will never be used to train your network. So in order to address the knockout problem, what we can do is we can choose a leaky ReLU. So if the value of x is greater than 0, we set it to x and set the other values to 0.01, so that at least in the training all nodes or all inputs should participate from the point of initialization. So it gives this shape, leaky ReLU, and we know that ReLU activation was in this format. Some of the other activation functions are tanh. We have the sigmoid, then we have our ReLU activation, sReLU, and then we have ELU activation, soft plus, soft sign. Some of these you can further explore in your network for the activation functions. So sigmoid or softmax are not only the option for us, we can actually use ReLU or leaky ReLU or tanh, sReLU, different versions, and you can see the graphical representation of these activation functions. In order to address the problem of vanishing gradient, these are some of the solution. This is one of the solution is to choose first appropriate activation function and then setting your learning rate appropriate. So what we have studied here is that sigmoid function and their combination generally work well. However, they can be a vanishing gradient problem. So ReLU activation is mostly used these days. And if we encounter a case of dead neurons in our network, then we can use the ReLU activation. We can check that on how many nodes are participating in the training, and then if there is a problem of dead neurons, your links are not activated from the initialization point due to random initialization. So we can use another version of ReLU activation function, that is your leaky ReLU. And mostly we use ReLU activation in the hidden layer, and at the classifier layer we usually use softmax or sigmoid at the last layer, at the output layer. As a rule of thumb, you can begin with using ReLU function and then move over to other activation function in case ReLU doesn't provide the optimal results. The starting point is do not use sigmoid, or if your sigmoid is not giving you good results in all the hidden layers, you can use ReLU activation function to address the vanishing gradient problem in your deep networks. Next, we will study the good initialization for deep networks in the next lecture. So if you have any questions on today's lecture contents, you have any queries, you can comment and I will respond to it actively, or you could email me. And I will respond to your queries regarding these lecture contents.